Okay, in this problem, what we've got to do is prove that we get the sum of these terms equal to this expression. Now, what we're doing is having the fraction 1 over 2m minus 1 times 2m plus 1. So basically it's 1 over the product of consecutive odd numbers, and it comes up to 1 over 2m plus 1. So we've got to working this out by mathematical induction. So again, our first step is to show that it's true for n is equal to 1. So we substitute 1 into our equations, into our left-hand side, our general term, and sub it into our right-hand side. And we get that 1/3 is equal to 1/3, so it's true. So we assume it's true for n is equal to k. So our statement there, instead of n, we've got k in there. So that's what we'll be able to substitute in step 3. So that statement there will pop up and we'll be able to make our substitution. So in step 3, again, what are we required to prove? We're going to get either one of these statements. So k plus 1 over 2 lots of k plus 1 plus 1, which can be simplified to k plus 1 over 2k plus 3. So again, there's our sum to k terms that we start off with, and our k plus 1th term. So it's a little bit ugly to start off with. You can clean it up. So this statement here becomes equal to that sum from step 2, and then the 2k plus 1 minus 1 cleans up to 2k plus 1, and 2k plus 1 plus 1 gives us 2k plus 3. So again, we want to get it all as one sum, and we're aiming for what we've got up here. So we'll get a common denominator. Our common denominator would be 2k plus 1, 2k plus 3. So multiply this fraction by 2k plus 3 on top and bottom. So there you can see that expression there. Expand it out, we can't factorise. So we expand it out. We do want 2k plus 3 on the bottom. So when we factorise, I think we're going to get a 2k plus 1. And that'll leave us with k plus 1 as our other term. And that allows us to do the cancellation there. So that factorisation is that one there. Gives us the k plus 1 on 2k plus 3. Thus it's true. So second question here. Again, this time it's just the sum of 1 over the product of consecutive integers would be equal to 1 minus 1 over n plus 1. So again, start with n is equal to 1, show it's true. So 1 times 2, 1 minus 1 over 1 plus 1, we show that substitution. Comes down to a half is equal to a half, so it's true for the first term. So assume it's true for n is equal to k, so our sum to n for k terms is the left-hand side is equal to that right-hand side. And again, what are we going to be required to prove? We're going to substitute n for equals k plus 1. So we get the 1 minus 1 on k plus 1 plus 1, which is 1 minus 1 over k plus 2. So that's what we're going to look to prove. Again, we start off with our left-hand side and the sum to k plus 1 terms. So there's our sum to k terms, will be 1 minus 1 over k plus 1. Our sum to k plus 1 terms, our k plus 1 term comes out to 1 and k plus 1, k plus 2. Again, we want that 1 minus out the front. So we're going to keep that 1 minus, and we're going to perform that little operation we saw before where we group our fractions together in one, so we get the 1 minus some statement. But remember, when we factorise a negative out of a positive, it becomes a negative there. So we've got to be careful about that part there. So again, once we've got to that point, well, we just get a common denominator. The lowest common denominator would be k plus 1, k plus 2. Multiply this fraction by the k plus 2, k on top and bottom. So that's where we get the k plus 2 minus that 1. And do the subtraction, gives us the k plus 1 over k plus 1, k plus 2, which will cancel. Leaves us the 1 over k plus 2, which is what we're required to find. So just be careful. That's the tricky step there, is making sure that we factorise a negative out here, we get a positive, because a negative times a negative would give us that positive there. So in question 3, this one's a little bit different. So what have we got to be careful about? Really, the first term here really has nothing to do with our series. So we've got 1 over x minus 1, and then we've got minus 1 over x minus 1 over x squared. So our series basically starts from there. So, and comes down to 1 over x to the power of n is equal to 1 over x to the power of n x minus 1. Now it says for x greater than or equal to 2. Now I've actually done it for n is equal to 1 here. So remember, we have to establish that x has to be greater than 2, otherwise if x is equal to 1, then it's going to give us 0 there. So it's got to be, x has got to be greater than 2. That doesn't mean to say that n can't be 1. So we substitute n being 1 as just the first term. So 1 on x minus 1 minus 1 over x to the power of 1, because x to the power of n and n is 1. So we get our statement there. 1 over x to the power of n with x to the power of 1, x minus 1. And we were able to show that that's doing our substitute, our collecting of like terms, and once we get our common denominator, we're able to get it. Statement's true. So we assume it's true for n is equal to k. So again, remember this part's the series here. That's not really part of the series. But then our step, we've got our step sum there that's going to be equal to that expression. So again, we're going to start with the left-hand side. We want to prove that it comes down to 1 over x to the power of k plus 1 outside of x plus 1. So we get our sum of the first k terms, and then we're still subtracting the next 1 over x k plus 1, so the k plus 1th term. So there's our statement, there's our sum, 1 over x power of k, x minus 1, minus 1 over the k plus 1. Now, remember that this is x times x to the power of k. So really what we've got there is partly a common denominator. That's really x times x to the power of k. So we've got an x to the power of k in there. So really what we need is k plus 1. Multiply this by an x, and multiply this by an x minus 1. So that's why it becomes an x on the x plus k, x to the power of k plus 1 times x minus 1. And this one gets multiplied top and bottom by the x minus 1. So that's where the x minus 1 comes in there. Simplify our top, x minus x gives us 0, 1 minus times minus 1 gives us the 1, and there's our expression that we need, so therefore it's true, so we can make our step there. Have a look through the algebra there. That's a little bit tricky, that's different than what we've done before, so but we've got to be careful that we can make those manipulations of a common denominator.